wait, come back. So what happened?
The bus takes too long to come here.
It's 9:20. Okay, I'll let you off this time. You can sit down.
Thank you.
Yeah, I did that on purpose because I wanted to make a strong point that you have to read the question very carefully, because I even made the numbers the same in 5 and 6 so that it would look the same, and I was hoping or testing if you can notice a very small difference that actually affects the answer significantly. In number 5, the ball is not resting on anything, meaning that it's just moving in the air like this. In number 6, it's on a tabletop. And you're thinking, what the fudge? There's no difference there. What's the difference? And the difference is, in the second case, because it's resting on the table, there's an additional force in the diagram, a reaction force on the table surface. So in case 5, it's like this. And the only forces you have here are T and mg. But in question 6, it's like this. You have a T, an or, and an mg. The difference is here, that's T cos and that's T sine. That's T cos and that's T sine. In this picture you can say T plus T sine theta equals mg, but here you cannot say that. T sine theta plus or equals mg. So in fact, in this question, if I was only looking for the T, it's enough to do the Jerry trick and just look at the vertical. But you can't here, and the reason you can't is because you don't know the or.
But in the video you didn't solve out.
But in this pattern, if I what is also in T cos, I get the same T as T sine.
Do you? You use T cos and you got the same T? Well, it depends what you use for the angle. Did you measure the angle here? Here? But you said T cos equals mg. You got the same. Oh, you use T cos. That's it. Yeah, that's fine. Yeah, that should give you the same answer. It didn't. It should have. Did it match the answer at the back? No, but I have answer 5 and 6. And I got 21 newtons about.
Yeah.
What did you get? Ah, so the way you did it for the first one gave you the answer for the second one. So let's see what you did. What did you say for the first one? You said T cos theta . 10 times squared. Yeah.
But I have a question. Which angle am I supposed to use?
For this angle. Very interesting, Monica, because when I look at this picture here, I can make the same equation. Yeah, with the same angle. So I'm trying to figure out what's the difference between the two.
What's the difference? The first one don't have that reaction.
No, I know what the difference is, but my point is this formula is true for both stories, which means it should give you the same answer for both. But obviously, if you look at the vertical, that's not the case.
Different way to
This is a very interesting problem now. I can't understand.
This formula?
The only the only thing I can think of, Monica, is that perhaps I was wrong to think that the time could be the same for both. Maybe it's the case that I have the numbers wrong. Would the ball spin faster or slower if it was resting on the table? It should feel... This is very interesting. I'm quite confused now, which is good. It means we're learning. Guys, here's the issue with question 5 and 6. Monica looked at the horizontal direction, and by looking at the horizontal direction she made this formula, but this formula gives you the same answer for tension. But the way I did it in the video is I looked at the vertical. And I got different answers. Okay, let's write down the two equations. So in the first question, I can say T sine theta equals mg, and T cos theta equals 4 pi squared m or over T squared. And in this picture, yeah?
If, like the second one, you have to consider the R, but the T will still be the same. It changes just because the R is there.
The tension doesn't change? I feel like it should. These are the two equations.
Even if you look at the second one, the T sin theta plus R equals T cos theta.
I think I see what the problem is. In this picture, the or...
Yeah, R should be short.
Yeah, well, or the reaction is 0. Yeah. So my mistake was I shouldn't have kept all the numbers the same. By keeping all the numbers the same, even though I tried to make the question different, it is actually the same as the previous one. So that means one of my 5s and 6s is wrong. Which one do I want to make as the wrong one? And one of them is right. I will make number 5 right and number 6 wrong. Why?
Okay.
I just picked it at random.
But why is it?
It's not wrong. I mean, I shouldn't be saying the word wrong. I didn't do what I wanted to do. In number 6, the reaction is 0. That's the only way that these can be the same. But of course, if the reaction is 0, it's the same picture as this one, when it's not on a table. So what I wanted to do was make 2 different questions, one on a table, one not on a table. But by accident, I made 2 questions the same. One on a table, or one not on a table, and one not on a table. A bit unlucky for me. So I should not have made all the numbers the same. I should have changed this one here a little bit. Perhaps I should have made the time different for the circle here. That's what I should have done. If I changed the time, then it would change the tension, which is what I wanted.
Even if the right one, the T you get from T sin theta will be one the same as the T you get from T cos theta.
In this one?
Number 5.
Number 5 is that one. You don't get the same mathematical T.
You don't?
The first T sin theta you get 21, then you get T cos theta you get 41.
Okay, I know what's gone wrong now. I'm sorry, this is what we call in physics, my bad. I made up the numbers, so clearly what's happened is I've made up numbers that don't work. In other words, I thought I could pick any time, but I can't. I should have picked the time that made the answer you get from this equation the same as the answer you get from this equation. So this was my mistake. I thought I could choose any numbers, but it seems I couldn't have. Yeah. So what I should have done is, when I made this question, when I got the answer here, I should have put it here to work out what the time should be. Yeah?
Yeah.
Okay. What's next now? Now I know I got this answer right. I know.
Not really.
No, I did. It's definitely right.
Oh.
Good, okay, good. What's the debate about?
Why is your height?
Teacher, I also have some.
Hold on, Monica is talking, please. Go on, Monica is talking, please. Go on, Monica.
For me, if I was thinking about what the height is, I would think the height should be 2r because it is directly above.
The height is 2r initially.
Yes.
Initially, but the height changes.
Yes. But the height initially is 2r.
Correct.
And
Does this answer your question?
when you ask for the height at particular point,
Yeah. Was that it?
because the rest of my mathematics is
Okay. You use 2r throughout the question.
I think I get that.
Good. I suspect if you use 2r, your angle should be quite small.
14.
Yeah, 14. Yeah. What did you think of number 7? Yeah, which is great.
You can have, if you follow instructions.
Yeah, last year I didn't give instructions. I just said, what is the theta? And then I realized, no, that's too hard. I better give instruction steps. Yeah. So, if you ever got this in the exam, which I don't think so because it's quite hard, but if you did get in the exam, I would hope that they would do what I did, which was to give instruction steps. Do you know what I mean?
Maybe.
Yeah. Okay, I liked number 7. What I like about number 7 is, if I change the masses, the answer does not change. Because the answer you got does not depend on the mass, because at the end of the question, the mass is cancelled. Also, if I change the radius, the answer doesn't change, because the radius wasn't in the answer at the end. It cancelled out. And finally, I cancelled out the g, meaning the g doesn't matter. Meaning if I put this on the moon or on Mars, I would still get the same answer. Amazingly, it will still exit at the same angle, regardless of the shape, the size, or the planet. Yeah? Yes? Interesting? I think so. Like, you would feel like that if I did this on the moon, I should get a different answer because the g is different. But I don't. It's always going to be 49.19 degrees. Yeah? And this kind of is useful because it means, for example, as an engineering idea, imagine you had something made out of stone or whatever, or it doesn't matter what the story is, and it's raining. You know that the rain that hits on the top will exit at this angle, 49. So when the rain is pouring off, you can actually work out the angle it leaves the shape at. Why is this important? Well, it means that you know that this part here will be dry, and only this part up to angle 49 will be wet, because the raindrop is like a little ball that rolls on it. Now, in real life it'll be a little bit more than 49 because the raindrop kind of sticks to it, but it gives you the idea. and this top here will be wet and it rains, and here will be dry. So maybe this part here you need to make the material a little differently so that it doesn't wear, because what would happen over time is maybe the top wears a little bit because it gets wet. These are kind of like engineering ideas. But how to calculate this angle, as you can see, is not easy. Even though it's a simple idea, it's not an easy one. Yeah? Okay, continue. So I will change 5 and 6's numbers so that they make sense now. Question 1, I misread my own question. And question 2, I mistyped the decimal points. And question 3, I forgot my square. Having a bad day. Okay, let's continue anyways. I know, you're such a kind class.